Uh, Welcome to this talk where I'm going to introduce PyTorch3D and talk about some new things that have been added recently. Uh, so I'm Jeremy. I'm from Facebook AI Research in London. And this represents a team across Facebook AI Research in America and in Europe, in Paris and London. PyTorch3D is a library that has been around for a bit more than a year, um, providing various functionality for 3D vision in the PyTorch ecosystem. So, various things that you might want to do with a model, with a deep learning model that concerns 3D data. So, simple types of 3D data are meshes and point clouds, and we have efficient structures, data structures for dealing with batches of meshes and point clouds, and we have various operations that we provide with them. Um, uh, Let me some a major part of the library is differentiable rendering. So rendering has been around for a long time. It's taking some data about 3D 3D world, 3D objects, and synthetically producing what a picture of them would look like. So that might depend on their colors, the lights available, the viewpoints, etc., etc. So rendering famous rendering libraries are things like DirectX and OpenGL and things like that. So fundamentally, rendering is not a differentiable process. So, for example, the color of my shirt is very different to the color of my finger. When I move my finger a little bit, a pixel in the image that you see changes very sharply. So the color of a pixel is not differentiable with respect to the location of my finger. So differentiable rendering will have to involve approximations of what rendering looks like, and that's probably where the first big part of PyTorch3D comes in. So PyTorch3D hasn't invented differentiable rendering. It's a library that makes available various operations efficiently in this domain. So let me hide myself and start playing. So here I've downloaded some example data that has been provided kindly freely. So I've loaded up a textured mesh of triangles that describe a cow, a sort of cartoon cow, and I'm going to demonstrate and render. So here are some pictures of it, and here is an example of it rendered from many different viewpoints. So you can get a picture of this object as described. So we have a scene set up where you can actually see not only is there a cow, but some parts of the cow are more lit than others. There's a light in front of the cow, so the back is darker and the front is lighter. So if I do a single rendering of the cow, there are various things I can so in fact let me so a single render is pretty quick. So there are stages in this rendering, and the first stage is establishing which triangle will contribute to which pixel. So that's called rasterization, and then deciding based on the triangle that is seen by each pixel in the image that I've defined, picking the color, which is shading and blending. So let me change some things. So for example, if I ask the rasterizer to produce multiple faces for each pixel, then I can use this gamma number to define how transparent each pixel is. So in order to make things continuous, everything's going to have to be a little bit transparent, and everything's going to have edges which are a little bit less than well defined. So gamma is going to be related to the transparency. So if I increase gamma, we will become able to see parts of the back of the cow through the cow. So here you can, we're still looking at the front of the cow. This is the original viewpoint, but you can see the back. These splotches which seem irrelevant are splotches that belong to the back of the head of the cow in this case, and the back of the cow itself here are appearing on the front of the cow, and here are the cow's back legs. So a parameter in PyTorch3D is controlling how transparent things are in the image, and how transparent each face is. And we always have to allow in differentiable rendering for things to be a little bit transparent. So that's kind of built into our rendering system. Another part we can do is to allow everything to be a little bit blurry around the edges. So if I make, I can, I think I can do this and see everything a little bit blurry. So let me again only render one pixel. That might leave gaps, but what you can see is that some triangles are merged into nearby triangles, and the edges of splotches are less well defined. So this has shown some of the tricks of non-realism, I guess, that we have to introduce into a rendering pipeline that allows differentiability to be there. So the resulting image is roughly a differentiable function of the description of the scene that we start with. So an example, we have an example in our tutorials for PyTorch3D of learning the position of a camera that was used to render a scene from the scene description. But there are many other potential applications for differentiable rendering. You could imagine using differentiable rendering to improve a deep learning model that can predict 3D from 2D. So that's like the major question in a lot of research is, given an image or multiple images of a 3D object, predict the 3D object's shape. And differentiable rendering is obviously doing the opposite and is a much more well-defined question. But you could imagine training a deep learning pipeline to do the difficult question and improving it by with a loss that depends on how good is the rendering, and then optimizing that would require differentiating through the rendering. So recently we've done a lot of work to work with volume rendering, which is very popular. There are many models at the moment that consider 3D volumes as a function of space in terms of occupancy and color, or something more complicated, rather than thinking about meshes and point cloud data. So I'm going to introduce some of that functionality. So again, I'm working with the same model of a cow. So I've got 40 images of the cow made rendered in the same way. These are assume these are ground truth images of this cow. Here's 4 examples of them, and then we can define a we want to define a volume renderer. So we're going to imagine that we have a description of the cow in terms of occupancy and color at each point in space, and we're going to define a way to render it as a volume renderer so from our camera position, we're going to take rays through each pixel of our image that we want to create, and we want to integrate what each ray might see as it interacts with occupied parts of the volume. So these are initializing various parameters to make the renderer work. And so we define a model that we're going to optimize, which is going to take, so to learn volumes in occupancies and colors from these 40 images of the cow. It's what it's going to do as parameters. It's going to have these occupancies, these densities, and the colors, and to render, what it's able to do is render into the 40 camera positions to produce 40 images, and what we hope is that those images will end up matching our target images of the cow. So how does forward look in this model? We make a PyTorch3D volumes object with the densities being, well, so in fact the exponential of our parameter, which is going to be log densities, and the exponential of our colors, and we're going to call a volume renderer on this data. And we set up a loss, and then we're going to do an optimization where we iteratively improve the unknown densities and features by trying to make the loss between the predicted images after volume rendering match the input images that we have of this cow. And initially they look bad, both the silhouette of the cow, but as time goes on, they start matching better. So I'll interrupt this, and then finally we can generate an image of the volume just by running the renderer on all the camera positions, and we get an image. So what we've tried to provide in these new tools with volumes is a very pluggable way for people to play with new style models that use volume rendering techniques, where the way rays are cast, the way your model of volumes is defined, is something that you're very free to make up in your own way. All of that reflects the philosophy of PyTorch3D, where we provide components which, although optimized, are very easy for you to play with, modify, and improve for your own research and projects. Thank you very much for listening.